Right now, sunlight is either resting on your skin, waiting just outside your window, or already promised for tomorrow. That light is 8 minutes old. Before it ever left the sun, though, that same light spent something like 100,000 years finding its way out of the sun's own core, passing from atom to atom, absorbed and released, again and again, until it was finally free to travel in a straight line, 2 very different ages, for the exact same beam of light. Distance, it turns out, isn't just space. A handful of minutes, crossing the space between here and the Sunday. It grows quickly from there. A few years to the nearest star beyond our own, millions of years to the nearest large galaxy, billions to galaxies so far away their light is older than the Earth itself. And somewhere past all of that, at the very edge of what any instrument has ever managed to detect, the delay becomes almost the whole story. Distance and time, folding into a single number. Tonight we'll follow that escalation outward, one honest step at a time, the same way it actually happened. A handful of careful measurements, stacked patiently across 2 centuries, each one reaching a little farther than the one before it. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. So, let's begin. There's a smaller, closer version of that same delay, and it belongs to ordinary weather rather than the stars. Sound travels through air at its own small, ordinary fraction of light's speed, close enough that a nearby voice feels instant, far enough that thunder settles in a beat or two after the lightning that caused it, once a storm sits far enough away to notice the gap, the same quiet lag at a human scale. Sit with the sunlight a little longer, too. 100,000 years is longer than the entire history of anatomically modern humans. Every person who has ever lived, every fire ever lit, every word ever spoken, fits comfortably inside the time one photon spent finding its way out of its own star. And that was only the nearest star we have. Light from the moon takes a little over a second to reach you. Light from the far edge of our own solar system, out past Pluto, takes more than 5 hours. The next star beyond our own sun sits so far away that its light takes not hours, but years. 4 1/4 of them. To make the same crossing, by the end of tonight, that delay adds up to an actual number. The part of the universe we can currently see is about 93 billion light-years across. Nobody measured that with a ruler. It's built, rung by rung, out of much smaller, much quieter measurements. Some of them almost embarrassingly simple. Some of them barely 100 years old. And each time astronomers thought they had finally found the true size of everything, the universe turned out to be a little bigger than that. We're going to walk that ladder together, one rung at a time, starting absurdly close to home with the nearest star beyond our own Sunday. It sits 4 1/4 light-years away, and we know that number the same way a surveyor knows the width of a river, not by crossing it, but by looking at it from 2 different points and letting geometry do the rest. A light year, in case the word hasn't quite earned its meaning yet, isn't really a length. It's a length disguised as one. Built from how far light can travel in a single year at just under 300,000 kilometers every second. Every distance in tonight's story will come dressed the same way. A number that looks like a size, but is quietly an age underneath. This method is called parallax, and it's the same quiet trick a pair of eyes performs constantly, without anyone ever noticing. A finger held at arm's length, seen first through one eye and then the other, seems to jump against whatever sits behind it. Not because the finger moved, but because each eye happens to be looking from a slightly different point, a few inches apart. The closer the finger, the bigger that small, invisible jump held nearer the face the jump grows larger still. Held as far out as an arm can reach, it shrinks toward almost nothing, fading the farther out it goes. That relationship, the jump shrinking as distance grows, holds with perfect mathematical consistency at any distance at all, which is exactly the relationship astronomers lean on, carried out to a baseline far wider than any arm could ever stretch. Astronomers use the same quiet geometry, except their 2 points are opposite sides of Earth's orbit around the Sun, separated by about 186 million miles, instead of a few inches. A nearby star, its position recorded once in January and again in July, will have drifted very slightly against the far more distant stars behind it. An apparent wobble so small it's measured in fractions of an arcsecond, but real and geometric, and almost embarrassingly simple once it's understood. The size of that wobble, run through the same trigonometry that finds a building's height from its shadow, gives the distance. No assumptions about brightness, no models of how stars work, just angles. Nobody managed to actually measure one of these wobbles until 1838, which is startling when you remember how long astronomers had already spent staring at the sky. That year, a Prussian mathematician and astronomer named Friedrich Bessel finally detected the parallax of a faint, fast-moving star called 61 Cygni and calculated its distance at a little over 10 light-years. Modern instruments have refined that number slightly. The accepted distance today is closer to 11.5 light-years, but the method itself has barely changed since Bessel's desk. It was the first time in history that a human being held a real, geometrically certain number for the distance to another star, rather than a guess dressed up in Latin. That's the same method behind the 4.25 light-year distance to Proxima Centauri, refined over the last decade by a spacecraft called Gaia, which has spent years quietly measuring the parallax wobble of more than 1 billion stars at once. Some of them thousands of times fainter than anything visible to the naked eye. For the nearest, brightest stars, the ones close enough for the wobble to still be measurable, Gaia's numbers are accurate to a fraction of a percent, which means that if you remember only one number from tonight, it can be this one. 4.25 light-years to the nearest star beyond our own sun. And we know it not because someone estimated it, but because we watched it shift. It is worth knowing that this simple trick, angles and patience, is also one of the oldest unsolved problems in the history of astronomy. Ancient Greek astronomers understood the logic of parallax perfectly well over 2,000 years ago. If Earth genuinely moved around the Sun, they reasoned, the nearby stars should shift against the background exactly the way a finger shifts against a wall. They looked for that shift with nothing but careful naked eye observation, generation after generation, and found nothing. For a long time, that absence of any visible shift was treated as solid evidence that Earth stood still, because a wobble too small to see seemed like a strange thing for nature to hide on purpose. The wobble was never actually absent. It was simply far smaller than anyone had imagined a star's distance could demand. Even the nearest stars sit so overwhelmingly far away that their entire parallax shift, viewed from opposite sides of Earth's orbit, amounts to an angle smaller than a single arcsecond. Smaller, from Earth, than the width of a coin would appear from over a mile away. No naked eye, no matter how patient or how well trained, was ever going to catch that. It took until 1838, and a telescope precise enough to measure angles that small, for Bessel to finally close a question that had sat open, quietly, for 2,000 years. The stars weren't hiding their motion. They were simply that much farther away than anyone had dared to guess. And it took 2 millennia of instruments slowly improving before the universe's honest answer became visible at all. That is one true rung. Solid, verifiable, built from nothing but angles and patience. It is also, it turns out, almost useless for anything bigger than our own galactic backyard. And understanding exactly where this method runs out of road is the fastest way to understand why the universe needed several more rungs before anyone could speak honestly about its size at all. Even that number, 4.25 light-years, is easy to say and almost impossible to actually feel. Try it a different way. If you built a scale model of just the Sun and Proxima Centauri, shrinking the Sun down to the size of a grain of sand, Proxima Centauri would be another grain of sand, roughly 4 miles away, with nothing but empty space. No other grains at all, filling the entire distance in between. That is the nearest star. Not a crowded neighborhood, a single, faint neighbor 4 miles off, across a stretch of nothing so complete that it makes an ordinary human sense of far away feel almost embarrassingly small by comparison. Rest with that thought for a moment. One star 4 light-years out, pinned down by nothing more than geometry and the width of Earth's orbit. It is a small, solid fact to hold on to in the dark, and it is also, quietly, the first stone in a much longer road. Before any of that could work, though, astronomers needed to know the actual length of their own baseline, the true width. In real, physical units like miles or kilometers of Earth's orbit around the Sunday. Parallax only gives you a distance once you know exactly how far apart your two observing points are, and for a long time, nobody had a reliable, direct answer to how far Earth actually sits from the Sunday. That number came from a completely different, much rarer kind of celestial event, the transit of Venus, when Venus passes directly between Earth and the Sun and appears, briefly, as a small dark dot crossing the solar disk. Astronomers in the 1760s, following a method proposed by Edmund Halley decades earlier, coordinated observations of a transit from widely separated points on Earth, timed the tiny differences in exactly when and where each observer saw Venus cross, and used that difference, along with the same triangulation logic behind stellar parallax, to finally calculate the Earth-Sun distance in real, physical units. It took 2 separate transits, expeditions scattered across the globe, and years of careful calculation to settle on a reliable figure. Only once that baseline existed in real, trusted units could Bessel's later stellar parallax measurements convert their tiny angles into actual light-years, rather than just relative comparisons. That wobble gets smaller the farther away a star sits, which is simple geometry, but it creates a hard problem. Move a star twice as far away, and its parallax wobble shrinks to half the size. Move it 10 times farther, and the wobble shrinks to 1/10. At some distance, the wobble becomes smaller than any instrument can reliably detect, and the method doesn't fail gently. It simply stops giving you a usable number at all. For most of the 20th century, that ceiling sat uncomfortably close. Ground-based telescopes, squinting through the blur of Earth's own atmosphere, could only trust parallax measurements out to a few hundred light-years before the wobble disappeared into noise. The first real fix came earlier than you might expect. In 1989, the European Space Agency launched a smaller satellite named Hipparcos, the first spacecraft built specifically to measure stellar parallax from orbit. Above the atmosphere's blur, over roughly 4 years, Hipparcos measured accurate distances for about 100,000 stars, an enormous leap forward from ground-based telescopes, and a clear proof that doing this work from space, rather than through the shifting, distorting air above every ground-based observatory. Then, in 2013, the European Space Agency launched a far more ambitious successor named Gaia specifically to push that same idea much, much further. Gaia carries no camera pointed outward at planets or nebulae. Its entire mission is to sit in space, far above the atmosphere's distortion, and stare at the same stars over and over for years, timing their tiny seasonal shifts with a precision that would be like measuring the width of a human hair from 1,000 miles away. Gaia doesn't orbit Earth the way a weather satellite does. It sits at a quiet gravitational balance point called L2, nearly 1 million miles out, trailing Earth's own orbit around the Sun, slowly spinning so that its 2 telescopes sweep continuously across the entire sky, From that vantage point, shielded from Earth's own light and heat, it has spent over a decade doing one thing, over and over, with almost inhuman patience, measuring the exact position of the same stars again and again, and watching for the tiny seasonal shift that reveals their distance. Gaia has now measured parallax distances for more than 1 billion stars. For the nearest and brightest among them, the numbers are extraordinary, accurate to a fraction of a percent, the same quality of certainty that pinned down Proxima Centauri. But that precision fades with distance, and fades quickly. Reach out to a few thousand light-years, and the wobble has already shrunk to the edge of what even Gaia can trust. Reach out further than that, and the technique that gave us our first honest rung simply runs out of angle to measure. There's a way to feel that ceiling rather than just hear the numbers. Imagine shrinking the distance from the Sun to Proxima Centauri down to a single step. One footstep, and you've crossed 4¼ light-years. At that same shrunken scale, walking all the way across the Milky Way, edge to edge, would take you roughly 25,000 steps, day and night, without stopping. Gaia's most trustworthy measurements, the ones with the least uncertainty attached, reach perhaps a few hundred of those steps before the wobble becomes too small to trust. A few hundred steps out of 25,000, and that's just across our own galaxy. A galaxy that is itself, as tonight is about to keep proving, a small and undistinguished speck among countless others. Even our own spacecraft agree with that sense of scale, in their own slow, patient way. The Voyager probes, launched in 1977 and still, decades later, quietly sending faint signals home across the growing dark, are the farthest human-made objects from Earth, and after all that travel at tens of thousands of miles an hour, they have covered a distance that light crosses in less than a day. At that pace, reaching even the nearest star would take tens of thousands of years. Geometry can measure the gap in an afternoon of careful watching, comparing one small shift in starlight against another. Machines, moving as fast as anything we have ever built, would need longer than recorded human history just to physically cross the same distance. Here is what makes that ceiling humbling. Our own galaxy, the Milky Way, is commonly estimated to stretch on the order of 100,000 light-years across its main disk, though the outer edges are faint and ragged enough that different surveys draw the boundary in different places. Even taking the more conservative figure, Gaia's most trustworthy geometric distances only reach a small fraction of that span. The single most reliable, least assumption-dependent method astronomers have. Pure angles, no models, no guesses about brightness, cannot even measure all the way across our own home galaxy. It runs out of road inside our own neighborhood, long before it reaches the edge of the room we actually live in. Even within its limits, that partial reach has been enough to uncover things nobody expected to find. By combining the distances and motions of millions of individual stars, astronomers using Gaia's data identified a distinct population of stars moving on unusually stretched, elongated orbits through our galaxy's inner regions. The leftover debris, it turned out, of an entire smaller galaxy that collided with the Milky Way roughly 8 to 11 billion years ago and was slowly torn apart and absorbed. Astronomers now call that ancient collision the Gaia sausage, after the elongated shape its stars trace through velocity space, and it stands as a quiet reminder that even a method with a hard ceiling on distance can still, within that ceiling, rewrite the history of an entire galaxy. There's a second, quieter obstacle sitting inside that same distance, one that has nothing to do with the wobble at all. Our galaxy's disk is threaded with clouds of dust and gas, faint enough to be invisible against a dark sky, dense enough over thousands of light-years to dim and redden starlight passing through it, the same way distant streetlights blur and warm in color on a foggy night. Even if a star's wobble were large enough to measure precisely, a thick enough curtain of galactic dust between here and there can make the measurement unreliable in a completely different way. Distance, it turns out, isn't only a question of how far. It's also a question of how much stands in the way. None of that is a knock against the method itself, and it's worth being fair about that before moving past it. Parallax does exactly what geometry promises. With no exceptions and no fine print, every single time it's tried, at any distance where the wobble is still large enough to catch, it simply cannot see far enough to answer the question tonight is actually asking. Somewhere out past a few thousand light years, in the vast remainder of even our own galaxy, a different kind of measurement had to take over. One that didn't rely on watching something shift, but on understanding, in detail, what a star was actually doing. And here is the part worth holding on to as we climb. Every single rung tonight, visits from here forward, still owes its trustworthiness back to this first one. Whatever new trick comes next has to be checked. At some point, against a distance parallax can measure directly, calibrated against the one method that needs no assumptions at all before it's trusted to reach any farther. The latter only works because each new rung stands on the one below it, and the very first rung, the one built from nothing but geometry, never stops being the foundation everything else quietly depends on. That measurement began, unglamorously, with a woman counting photographs in a basement in Massachusetts. In the early 1900s, the Harvard College Observatory employed a team of women paid a small hourly wage to examine thousands of photographic glass plates of the night sky and catalogue what they found. They were not permitted to operate the telescopes. Their job was to sit with a magnifying lens and a stack of exposed plates, comparing star to star, night to night, and recording anything that changed. It was slow, exacting, poorly paid work, and it is where one of the most important discoveries in the history of measuring the universe quietly happened. The observatory's director, Edward Pickering, had assembled this team after growing frustrated, according to observatory law, with the pace of his male assistants, reportedly remarking that his housekeeper could do the work faster. Whether or not the story is told exactly as it happened, the women he hired afterward, later remembered as the Harvard computers, did carry out work that shaped astronomy for the rest of the century, cataloguing hundreds of thousands of stars from photographic plates, sorting and measuring what the observatory's telescopes had already captured, but no one had yet had the patience to read. One of those women was Henrietta Leavitt. Her assignment was to study a class of stars called Cepheid variables, stars whose brightness visibly rises and falls in a regular, repeating rhythm like a slow, steady pulse. In a pair of small, faint smudges of light visible from the southern hemisphere, called the Magellanic Clouds, Leavitt didn't know at first how far away the Magellanic Clouds actually were, but she noticed something that turned out to matter more than knowing their distance outright. Among the Cepheids she catalogued, the ones that pulsed more slowly were also, consistently, the brighter ones. That relationship pulse period tied directly to true brightness is not obvious, and it is not a coincidence of any single star. It comes from the physics of how a Cepheid actually works. A star in this particular late stage of its life becomes unstable, its outer layers alternately trapping and releasing heat, causing the whole star to swell and shrink in a rhythm set by its own size and mass. Bigger, more luminous Cepheids swell and shrink more slowly, the same way a larger bell rings at a lower, slower tone than a small one. Leavitt didn't know all of that physics yet. What she had was something almost as good. A pattern, quietly holding across dozens of stars, precise enough to plot as a clean, believable curve. She published that curve in 1912 in a short paper listing the periods of 25 variable stars in the small Magellanic Cloud, because all of those stars sat at roughly the same distance from Earth, bundled together in the same small, distant cloud. Any difference in how bright they appeared had to come from a real difference in how bright they actually were, not from some of them simply being closer. That let Leavitt isolate the relationship cleanly. Period tells you true brightness. No distance information required. It's worth pausing on how unglamorous the actual discovery process was. because it matters for how much trust the result deserves. Leavitt wasn't running an experiment or testing a hypothesis handed to her by someone else. She was doing inventory, comparing plate after plate, star after star, marking down which ones brightened and dimmed and by how much, for what was, at the time, simply considered careful bookkeeping rather than groundbreaking physics. The pattern she found wasn't something she went looking for. It was something that became impossible not to notice. Once enough careful, patient counting had actually been done, some of the most important measurements tonight started exactly that way. Not as a bold hypothesis chasing glory, but as ordinary, careful attention sustained for long enough that a real pattern had no choice but to surface. Here is why that single relationship turned out to be worth more than almost any single measurement in the history of astronomy. If you know a star's true brightness, and you can measure how bright it appears from Earth, the difference between those two numbers gives you distance. A candle held a few feet away looks brighter than the same candle held across a football field, and the amount by which it dims tells you precisely how far it has receded. As long as you already know how bright that kind of candle burns up close, Leavitt had just handed astronomers a candle whose true brightness they could read directly off its pulse. Astronomers call this a standard candle. Find a Cepheid anywhere, time its pulse, and you know how bright it truly is. Compare that to how bright it looks from here, and you have its distance. No parallax wobble required, no angle to measure, no ceiling imposed by the width of Earth's orbit. Cepheids aren't the only stars whose brightness rises and falls, which meant astronomers first needed a reliable way to tell them apart from other kinds of variable stars before trusting the relationship at all. A Cepheid's brightness doesn't simply flicker or wander unpredictably. It traces the same distinctive shape night after night, cycle after cycle, a fairly quick rise to maximum brightness, followed by a slower, more gradual fade back down, repeating with almost clockwork regularity over anywhere from a few days to a few months, depending on the individual star. That distinctive shape, plotted as a light curve, is itself part of the identification. A star behaving that precisely, that repeatedly, is doing something structural and predictable, not something random, and it is exactly that predictability, tested and confirmed across thousands of individual Cepheids, since Leavitt's original 25, that lets astronomers trust the brightness they calculate from a single number. How many days between one peak and the next? This is a genuinely different kind of measurement than the one we just spent an hour trusting. Parallax needed nothing but geometry. Pure angles, no assumptions about the star itself. A Cepheid's distance depends on trusting a pattern. That this particular kind of star behaves predictably enough, everywhere in the universe, for its pulse alone to reveal its true brightness. That is a larger claim than an angle. It needed to be tested and calibrated against parallax itself on the handful of nearby Cepheids, close enough for geometry to check the answer directly. It was repeatedly, by multiple astronomers, in the years after Leavitt's paper, and it held. That trust has only deepened since. Modern telescopes using a technique called interferometry, which combines light from multiple instruments to measure impossibly small angles, have managed to directly observe the physical swelling and shrinking of a handful of the nearest Cepheids as they pulse, watching their actual diameter change in real time rather than inferring it indirectly from brightness alone. The behavior matches Leavitt's century-old pattern precisely, a relationship discovered by counting photographs by hand, using instruments with no idea what a Cepheid physically was, has now been confirmed by watching one of these stars visibly breathe. What it bought, in exchange for that slightly larger claim, was reach. A star's apparent brightness can be measured accurately across distances where its parallax wobble is already too small to see at all. Cepheids are also unusually luminous stars to begin with, bright enough to be picked out individually in a smudge of light that, at the time, nobody was even certain was part of our own galaxy. Leavitt had built a candle bright enough, and predictable enough to be trusted far past the point where the first rung of the ladder had already run out. Other astronomers picked up Leavitt's relationship almost immediately, recognizing what it made possible before she herself was given the chance to chase it further. Ejnar Hertzsprung, a Danish astronomer, used her period-luminosity law within a year to calibrate distances to nearby Cepheids, using parallax, tying Leavitt's brightness-based candle back to the same geometric method Bessel had pioneered nearly a century earlier. The second rung checked directly against the first, and holding, not long after, the American astronomer Harlow Shapley used the same relationship to map the actual shape of our own galaxy for the first time, using Cepheids inside star clusters to show that the Milky Way was far larger than anyone had assumed, and that our own sun sat nowhere near its center, but out in a quiet, unremarkable stretch of one of its spiral arms. Leavitt's candle had already reshaped our understanding of our own galaxy's size and our own unremarkable place inside it, years before anyone pointed it at another galaxy entirely. Her method never became obsolete, either. Decades after Leavitt's original paper, one of the flagship projects of the Hubble Space Telescope, appropriately named after the astronomer who used her relationship to measure Andromeda, spent years in the 1990s doing essentially the same work she pioneered at a far greater distance, identifying Cepheid variables in dozens of galaxies well beyond our own local group, timing their pulses, and using them to pin down the local expansion rate of the universe with far greater precision than ever before. The James Webb Space Telescope has continued that same work since, finding and measuring Cepheids in galaxies fainter and farther than Hubble's instrument could resolve clearly, specifically to double-check the calibration at the heart of the disagreement. Tonight is going to circle back to later. A method invented to catalogue variable stars in a nearby smudge of light using nothing but a magnifying lens and careful bookkeeping is still, more than a century later, one of the most trusted tools in modern cosmology. She never got to use it herself for the discovery that would make it famous. Leavitt died in 1921, having spent her career on an hourly wage, doing work that male astronomers of her era were free to build careers upon. In 1925, a Swedish mathematician attempted to nominate her for the Nobel Prize in Physics, having learned of her period-luminosity law and its importance to the growing field, only to be informed that Leavitt had died 4 years earlier. The Nobel Committee does not consider posthumous nominations, and the recognition that might have come her way simply arrived too late to reach her at all. It fell to someone else, a decade later, standing at one of the largest telescopes on Earth, to point that candle at a smudge of light in the constellation Andromeda and ask a question that had, until then, divided the entire field of astronomy. Was that faint spiral of light part of our own galaxy at all, or something else, entirely, out past its edge? In the early 1920s, astronomers were genuinely divided over a question that sounds almost quaint now. Was our galaxy the entire universe, or just one of many? The Milky Way was assumed by many to contain everything. Every star, every faint smudge of light, every nebula ever photographed, spiral-shaped patches of light like the one in the constellation Andromeda, were treated, by most working astronomers, as clouds of gas somewhere inside our own galaxy, simply too far out to resolve into individual stars. A smaller number of astronomers disagreed, arguing that these spirals were something far stranger. Entire separate galaxies, island universes, sitting at almost unimaginable distances beyond our own. This disagreement had a name. Astronomers called it the Great Debate, and it came to a head in 1920 at a public meeting of the National Academy of Sciences in Washington, where the astronomer Harlow Shapley, the same Shapley who had just used Leavitt's Cepheids to map the true size of our own galaxy, argued that the spiral nebulae had to be relatively small and nearby comfortably contained within an unusually large Milky Way. Arguing the opposite side was Heber Curtis, who held that the spirals were genuinely separate island universes, roughly comparable in size to our own galaxy, sitting at truly enormous distances beyond it. Both astronomers were careful, credentialed, and working from real data. Neither had a way to actually measure the distance in question, which meant the debate, for all its rigor, it had no way of being settled, because nobody yet had a method that could measure a distance that large. Edwin Hubble had that method, or at least, he had access to the largest telescope in the world and Leavitt's candle in hand. The instrument he used, the Hooker telescope at Mount Wilson Observatory in California, had a mirror 100 inches across, ground and polished with a precision that took years to achieve, and it would remain the largest working telescope on the planet for nearly 3 decades after Hubble's discovery. Working at that observatory through 1923 and 1924, Hubble spent months photographing the Andromeda Nebula, searching its faint outer regions for individual stars whose brightness rose and fell in the unmistakable, repeating rhythm of a Cepheid. He found one, then several more. He timed their pulses, calculated their true brightness using Leavitt's relationship, compared that to how faint they actually appeared through his telescope, and did the arithmetic that the period-luminosity law made possible. One of Hubble's original glass photographic plates from that search still survives, and on it, next to one particular point of light, he had initially written N for nova, a star that flares briefly and fades. Comparing that plate against earlier photographs of the same region, he realized the star wasn't a one-time flare at all. It brightened and dimmed on a repeating schedule, the unmistakable signature of a Cepheid. Hubble crossed out the N and wrote, in the margin, var, variable. With an exclamation point he rarely allowed himself. It is a small, human mark on a piece of glass the moment a career astronomer, alone with a photographic plate, realized he was about to end a debate that had divided his entire field. The answer stopped the debate cold. Andromeda was not a nearby cloud of gas inside our own galaxy. It was an entire galaxy in its own right, sitting so far beyond the edge of the Milky Way that our own galaxy's full 100,000 light-year width barely registered as a rounding error by comparison. The universe was not one galaxy. It was, at minimum, 2, and if there were 2, there was almost certainly no reasonable limit to how many more might be out there. Each one its own island, each one impossibly far from every other. Hubble's original distance for Andromeda, based on the tools available to him at the time, was too small. By roughly half. The error wasn't sloppiness on his part. It came from something nobody yet understood. Cepheid variable stars actually come in 2 distinct populations, born from different generations of stars with slightly different chemical makeups, and each population follows its own separate period-luminosity relationship, offset from the other. Leavitt's original calibration, built from the stars available to her, mixed the 2 populations without knowing it. Hubble, using that same calibration, was one honest step removed from a subtlety nobody could have caught yet. It took until the early 1950s for the German-American astronomer Walter Baade, working through the calibration with sharper instruments and a deeper understanding of stellar populations, to isolate the 2 separate Cepheid relationships and correct the error. When he did, the accepted distance to Andromeda roughly doubled overnight. And so, in effect, did the accepted scale of the entire universe. Every galaxy distance calibrated against the old, uncorrected relationship needed to be revised outward, all at once, by the same startling factor. This is worth sitting with, because it is the first real example of something that is about to happen again and again on this ladder. A rung gets built, it gets trusted, it gets used to measure enormous distances with real confidence, and then, sometimes decades later, a subtlety inside the rung itself gets discovered, and the whole scale of the universe quietly shifts beneath everyone's feet, all at once. Not because anyone was careless, because the universe kept turning out to hold one more layer of detail than the previous measurement had accounted for. Modern instruments, calibrated against Bardé's correction and refined many times since, place Andromeda at a distance of approximately 2.5 million light-years, a number so far beyond a human intuition for distance that it is easier to describe what it means than what it looks like. Light leaving Andromeda's stars tonight, traveling at the same speed that got sunlight to your skin in 8 minutes, will not reach Earth for 2.5 million years. The light arriving at your eyes right now, if you could actually see Andromeda from where you're lying, left that galaxy before a single member of our own species existed to look up and notice it. Andromeda is also, despite how faint it looks, physically enormous across our sky. Measured from end to end, its faint spiral arms span an angular width several times wider than the full moon appears overhead. You simply can't see most of that width with unaided eyes because it's spread so thin and dim across such a wide patch of sky that only its bright central core registers as a single soft smudge. The galaxy isn't small and distant so much as enormous and distant, its true size hidden by how thoroughly 2.5 million light-years of distance dims an object that large. And yet, on a clear night, far enough from city light, you can still find that smudge without any instrument at all, visible to ordinary human eyes. It is the single most distant object most people will ever see unaided in their entire lives. And for nearly all of human history, everyone who looked up and noticed that smudge had absolutely no way of knowing they were looking at another galaxy at all, let alone one whose light had already been traveling for 2.5 million years before it reached them. There's one more thing worth knowing about that particular galaxy, and it's the closest tonight comes to a genuine plot twist. Andromeda and the Milky Way aren't just neighbours sitting quietly at a fixed distance from each other. Careful measurements of Andromeda's motion show it is actually falling toward us, closing that 2.5 million light-year gap at roughly 250,000 miles an hour, and current models suggest the two galaxies will eventually merge, somewhere on the order of 4 to 5 billion years from now, long after our own sun has changed in ways that will already have ended life on Earth as we know it. It is not a collision in any violent, catastrophic sense. The actual stars inside each galaxy are spaced so far apart that the two galaxies will pass through and around each other over hundreds of millions of years, gradually merging into a single, larger galaxy without a meaningful chance of any two individual stars actually striking one another. The most distant object visible to the naked human eye is also, quietly, on a multi-billion-year collision course with our own galactic home. Andromeda isn't even the only other large galaxy sharing our small patch of the cosmos. A third major spiral, the Triangulum galaxy, sits not far beyond Andromeda in the sky, smaller and fainter, visible only under unusually dark conditions, but a full-fledged galaxy of its own, likely caught in a slow gravitational dance with Andromeda that has probably shaped both galaxies' spiral arms over billions of years. Between the Milky Way, Andromeda, Triangulum, and dozens of far smaller dwarf galaxies bound loosely to one or the other, our local group holds somewhere in the neighbourhood of 100 known member galaxies. Modest, by the standards tonight is about to reach, but already far more crowded than the one galaxy, alone in an empty universe. Picture that had held for nearly all of recorded human history, before Hubble's Cepheids finally broke it open. That whole crowded little neighbourhood has a formal name. The local group, a small cluster of gravitationally bound galaxies together with dozens of smaller companions. Among them, quietly, the very same Magellanic Clouds where Leavitt first noticed her Cepheids pulsing, close enough to our own galaxy to be visible from the southern hemisphere without a telescope at all, orbiting the Milky Way the way a moon orbits a planet. The pattern that measured the whole universe was first noticed in our own galaxy's own backyard. A genuine neighbourhood, in cosmic terms, though neighbourhood here still means millions of light years between the houses. Two galaxies had just become dozens, and dozens it would turn out within a handful of years, We're about to become something far larger and far stranger. Not a cluster, but a system of clusters. All of them moving, all of them, for a reason nobody expected, retreating from each other at once. Once Hubble had proven that galaxies existed beyond our own, he turned the same telescope toward dozens more of them and began measuring something else entirely. Not just how far away they sat, but the color of their light. Every element in a star, when it burns, releases light at very specific, well-known wavelengths, a kind of fingerprint, identical no matter where in the universe that element happens to be burning. When astronomers point a telescope spectrograph at a distant galaxy, they can compare the fingerprint they see to the fingerprint they'd expect from hydrogen, or helium, or any other familiar element, and check whether it lines up. A single fingerprint could be a fluke, a stray reflection, a flaw in the instrument, a coincidence of one particular wavelength. What made the pattern trustworthy was that it wasn't a single line moving. Every element's whole set of fingerprint wavelengths, dozens of them at once, shifted together by the same proportion every time. It can't quietly move 40 of them, in lockstep, by exactly the same amount, in galaxy after galaxy after galaxy. For almost every galaxy Hubble measured, it didn't line up cleanly. The fingerprint was there, unmistakably, but shifted, stretched toward the red end of the spectrum, as though every wavelength of light from that galaxy had been pulled slightly longer than it should have been. Astronomers call this redshift, and by 1929, working with a colleague named Milton Humason, Hubble had measured it across enough galaxies at enough different distances to notice a pattern too clean to be coincidence. The farther away a galaxy sat, the more its light was redshifted. Not randomly, proportionally. A galaxy twice as far away showed, on average, almost exactly twice the redshift. The most obvious explanation, at the time, was the same one you'd reach for if you heard an ambulance siren drop in pitch as it drove away from you. The galaxies were simply moving away from us, and the light itself was being stretched the way sound gets stretched by a receding source, an effect physicists already had a name for. That explanation isn't wrong, exactly, but it undersells what was actually happening, and it took a few more years of careful thinking, following Einstein's equations for how mass and energy shape space itself. For the fuller picture to take hold, the galaxies were not, for the most part, moving through space the way a car moves down a road. The space between them was stretching, carrying the galaxies along with it, and stretching the light in transit right along with everything else. Picture a long, loose spring, the kind of coiled toy that can walk itself down a staircase, with a simple wave drawn along its coils from one end to the other. Stretch the spring evenly along its whole length, and that wave stretches with it. Not because the wave itself did anything, but because the medium it was drawn on got longer while the wave sat still relative to its own coils. Light behaves the same way as it crosses expanding space. A photon leaves a distant galaxy with a certain wavelength, and space itself lengthens underneath it, coil by coil, for the entire time that photon is in transit. By the time it reaches a telescope on Earth, its wavelength has stretched along with the space it crossed, shifted toward the red end of the spectrum by exactly the amount that stretching demands. The light didn't slow down or lose energy through friction. The ruler it was traveling across simply got longer while it traveled. That distinction matters enormously once you start thinking about the size of the universe. And it's worth sitting with the difference directly. If galaxies were simply flying through a fixed, unchanging space, their speeds would have some sensible upper limit, and there would be an obvious, single point they were all flying away from. But if space itself is the thing expanding, uniformly, everywhere at once, there is no explosion, no single center, no point in the universe you could stand at and correctly say this is where it all began, and everyone else is running away from me. Every galaxy, on average, sees every other sufficiently distant galaxy receding from it in every direction for the same reason a dot painted on a balloon watches every other dot recede as the balloon inflates. Not because any dot is special, and not because the dots are sliding across the rubber, but because the rubber itself, everywhere, is getting bigger. This is also, quietly, the reason a light year kept turning out to be the right unit for absolutely everything in this story. Rather than a simple measure of length, you could lay end to end like a ruler. If space itself stretches while light is crossing it, then the distance a photon started its journey at, and the distance to that same point, by the time the photon finally arrives, are two different numbers. Sometimes very different. For light that has been traveling long enough, we'll come back to exactly how different, because it turns out to be one of the strangest, most disorienting facts tonight. For now, hold on to the shape of the idea. Redshift isn't just evidence that the universe is big. It's evidence that the universe is still, right now, quietly becoming bigger in every direction, all at once, including the direction your own galaxy happens to be facing. Hubble wasn't actually the first person to reach this conclusion either, though he is the one most often credited with it. 2 years earlier, in 1927, a Belgian physicist and Catholic priest named Georges Lemaitre had already worked through Einstein's equations and proposed, from theory alone, that the universe should be expanding and that a proportional relationship between a galaxy's distance and its recession speed should exist as observational proof of it. His paper, published in a relatively obscure Belgian journal and largely overlooked at the time, anticipated Hubble's later observational result almost exactly. It took years, and a later, clearer English translation of Lemaitre's work for the astronomical community to properly recognize how much of this discovery had already been reasoned out on paper before anyone pointed a telescope at the right set of galaxies to confirm it. This news arrived as a genuine surprise, even to the physicist, whose own equations had already predicted it. When Albert Einstein first worked out the consequences of general relativity for the universe as a whole, years before Hubble's measurement, his equations kept implying that space should be either expanding or contracting, never sitting perfectly still. Uncomfortable with that implication, and assuming, like nearly everyone else at the time, that the universe was static and unchanging, Einstein added an extra term to his own equations, a kind of counterbalancing pressure, specifically to force the math to describe a universe that stayed the same size forever. Once Hubble's redshift measurements showed the universe was expanding after all, Einstein reportedly removed that extra term and, according to colleagues who discussed it with him afterward, referred to having added it in the first place as one of the biggest blunders of his career. The universe hadn't needed correcting. His instinct about what a universe should look like had. Hubble's law, as this relationship came to be called, gave astronomers something parallax, and Cepheids alone never could, a way to estimate distance using nothing but the color of a galaxy's light. Redshift doesn't fade the way apparent brightness fades, and it doesn't require finding an individual, resolvable star inside a distant smudge of light. It just requires enough light from the galaxy as a whole to read its spectrum clearly. That is a genuinely different kind of reach than either of the first two rungs offered. And it is the rung that finally let this ladder start climbing toward distances measured not in millions of light years, but in billions. But Hubble's law needed its own kind of anchor to be useful. A way to convert this galaxy is redshifted by this much into an actual distance in light years, rather than just a relative ranking of near and far. That conversion factor is called the Hubble constant, and pinning it down precisely turned out to be its own decades-long story. One tonight is going to circle back to later because the argument over its exact value has never fully closed. Even now. What mattered immediately, in 1929, was simpler and more startling than any single number. The universe was expanding everywhere, all at once, and had apparently been doing so for a very long time, which raised an obvious, almost unavoidable question. If everything is moving apart right now, what did it look like billions of years ago when all of that same material was closer together than it is tonight? Not every astronomer accepted the expanding space explanation right away, and it's worth giving the strongest alternative its due, the way any real investigation should. The Swiss astronomer Fritz Zwicky proposed in the 1920s that redshift might instead be caused by light simply losing energy as it crossed vast distances, worn down gradually by some unknown interaction with the emptiness of space itself. An idea that came to be called tired light. It was a genuinely serious proposal. And for a while, it competed honestly with the expanding universe explanation. What eventually settled the argument was a detail tired light couldn't explain. Distant type Ia supernovae, the same exploding stars we're about to spend real time on, don't just appear redshifted. Their entire explosion, the whole weeks-long rise and fade of their light curve, appears stretched out in time by exactly the same factor as their redshift. A supernova twice as redshifted takes twice as long, from our perspective, to brighten and fade. An expanding universe predicts that stretching automatically because time itself dilates along with the light. A tired light universe, where photons simply lose energy in transit without any actual stretching of space, has no honest way to explain why an explosion's duration would stretch too. The evidence didn't just favor expansion. It ruled its strongest rival out directly. Redshift could tell you a galaxy's distance once you trusted the conversion, but astronomers still wanted an independent way to check that conversion at truly enormous distances. A standard candle, like Leavitt's Cepheids, but bright enough to be seen not across millions of light years, but across billions. Cepheids, for all their usefulness, are still individual stars, and even the brightest ones fade below the reach of any telescope long before you reach the scale tonight is aiming for. Something far brighter was needed. It turned up, unexpectedly, in the deaths of stars rather than their lives. A type of stellar explosion called a type Ia supernova happens when a dense stellar remnant called a white dwarf, orbiting closely with a companion star, slowly pulls in extra material until it crosses a very specific mass threshold and detonates completely, all at once, in a runaway thermonuclear explosion. Because that detonation happens at almost exactly the same mass threshold every time, these explosions release almost exactly the same total amount of energy every time. For a few weeks, a single exploding star can outshine its entire host galaxy, bright enough to be seen from billions of light years away. The explosions aren't perfectly identical, but the differences between them turned out to be predictable in their own right. In the early 1990s, the astronomer Mark Phillips showed that the brighter a given supernova's peak, the more slowly its light fades afterward, a relationship precise enough to correct each individual explosion back to a common, trustworthy brightness. That correction, now called the Phillips relation, is what actually turns an ordinary stellar explosion into a usable standard candle, consistent enough, once properly measured, to work as Leavitt's candle scaled up to a cosmic size. In the late 1990s, two independent teams of astronomers, one called the Supernova Cosmology Project, led by Saul Perlmutter, the other the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, raced each other to answer the same question, using competing telescopes, competing data reduction techniques, and, by most honest accounts from people who lived through it, a fair amount of professional rivalry. That rivalry turned out to matter. In the end, in the opposite direction from what either team expected, because two competing groups, checking each other's methods with genuine skepticism rather than trust, arrived independently at the same, deeply unexpected answer. The result carried a kind of credibility that a single team's discovery never could have earned on its own. Both teams pointed this method at the most distant supernovae they could find, expecting to measure one specific thing: how much the universe's expansion had been slowing down over time, pulled inward by the gravity of everything in it. That was the expected result. Gravity pulls things together, and the leading models of the era assumed the expansion, whatever its current rate, had to be decelerating the same way a ball thrown upward slows as gravity fights its outward motion. The supernovae disagreed. The most distant ones appeared fainter, and therefore farther away than the decelerating model predicted they should be. Both teams checked their calibrations, checked for contaminating dust, checked every source of error they could think of, and the result held. In the years since, that original handful of distant supernovae has grown into a compilation of well over 1,000 carefully measured explosions, cross-checked across multiple surveys and observatories, and the accelerating trend the two original teams found has only grown more solid as the sample size has grown. The expansion of the universe was not slowing down. It was speeding up, accelerating, driven by something astronomers still don't fully understand and have. The discovery was strange enough, and confirmed carefully enough, that it earned the 2011 Nobel Prize in Physics for 3 of the astronomers who led the two teams. Nobody, including the cosmologists who study it professionally, currently knows what dark energy actually is. The simplest working model treats it as a fixed property of space itself, a constant amount of energy present in every cubic meter of the universe, regardless of how much that universe expands. Mathematically, the very same cosmological constant Einstein once added to his own equations and later regretted, now brought back for a completely different, evidence-based reason. Other researchers have proposed that it might instead be some kind of dynamic field, changing subtly over cosmic time rather than staying perfectly fixed, an idea sometimes given the name quintessence. Current data doesn't yet distinguish clearly between these possibilities, and several ongoing telescope surveys have been built specifically to measure whether dark energy's strength has shifted at all over billions of years, hoping to catch a preference between the two ideas. It's worth keeping this dark energy separate in your mind from a different, unrelated mystery with a confusingly similar name: dark matter. The unseen mass astronomers infer from the way galaxies rotate and clusters hold together gravitationally is a completely different puzzle, pulling things together rather than pushing them apart. Dark energy, whatever it turns out to be, is the one responsible for stretching space itself faster over time, and it's dark energy alone that matters for the rest of tonight's story about size and distance. Later, more precise measurements, including the same Planck mission we'll return to shortly, estimated just how much of the universe this mysterious dark energy actually accounts for, roughly 2/3 of everything that exists, by mass and energy combined with ordinary matter, the atoms making up stars, planets, and every reader of this sentence, accounting for only a small fraction of the remainder. We live, by these measurements, inside a universe whose dominant ingredient nobody can yet explain, and whose effects we can currently only detect by watching how it stretches the space between galaxies. Here is where that acceleration collides directly with everything we've built so far. And it's worth slowing down for, because this is genuinely one of the most disorienting facts available about the size of the universe. If space itself is stretching, and that stretching is accelerating, then a beam of light crossing billions of light years of it is not crossing a fixed distance. The space behind it keeps expanding even as it travels, which means the distance to wherever that light originally came from, measured today, is now considerably larger than the distance the light actually had to cross to reach us. It helps to remember, before going further, that every single thing said so far tonight has really been about the past, not the present. Whenever you look at anything, near or far, you are looking into how it was, by an amount that depends entirely on how far away it sits. A hand held in front of your face is a fraction of a billionth of a second old by the time you see it. The moon is a little over a second old. The sun, 8 minutes. Distant galaxies simply push that same small, ordinary delay out to its most extreme, honest conclusion. Take the most distant galaxy confirmed so far. As of this recording, an extremely faint, extremely early galaxy called JADES-GSZ140, confirmed through a 10-hour spectroscopic observation by the James Webb Space Telescope in 2024. Its light has been traveling toward us for roughly 13.5 billion years, meaning we are seeing that galaxy as it existed only a few hundred million years after the universe itself began. But because space has kept expanding for the entire 13.5 billion years that light spent in transit, that galaxy's actual position right now, if you could somehow ask where it currently sits rather than where its old light came from, is estimated at nearly 34 billion light-years away. Two true numbers for the same object. 13.5 billion light-years of travel time and almost 34 billion light-years of present distance. Neither number is wrong. They're simply answers to two different questions. How long ago did this light leave? And how far away is its source right now? And at cosmic scales, those two questions stop giving you the same answer. This is the detail that finally makes sense of the 93 billion light-year figure from the very beginning of tonight. The one we promised was real but hadn't yet earned. The observable universe's edge sits at that distance not because light has literally crossed 93 billion light-years to reach us. Nothing has traveled anywhere close to that far. Since the universe itself is only about 13.8 billion years old, a number we'll pin down precisely very soon. It sits there because the most ancient light we can detect, light that has been traveling toward us for nearly the entire age of the universe, originated from material that has since been carried by the ongoing stretching of space itself, out to a present distance of roughly 46.5 billion light-years in every direction. 46.5 billion out. Doubled for the full span across. Every rung on this ladder so far has been climbing toward the same honest conclusion. Distance, at these scales, is not a fixed line you could walk if you had enough time. It is a relationship between an object, a beam of light, and an amount of stretching that never stopped happening while that light was in transit. The universe is not merely large, it has been actively growing larger, in every direction, for the entire time any of this light has been on its way to you. Which means the true edge of what's out there, whatever it turns out to be, is not staying still long enough for any single number to describe it twice. Rest here for a moment. You don't need to hold the arithmetic. You only need to hold the shape of it. The light is old, the space it crossed kept stretching, and the two facts together are why, how far away, and how long ago stopped being the same question. Somewhere out past our own galaxy, a very long time ago, there is one piece of light older than any galaxy, older than any star, older than the elements that make up your own body. And unlike a galaxy, it doesn't sit in one direction. It surrounds us completely, arriving from every part of the sky at once. The same intensity no matter which way a telescope points. For its first few 100,000 years, the universe was too hot and too dense for atoms to exist in any stable form. Space itself was filled with a churning plasma of bare protons and electrons, and light generated in that plasma couldn't travel more than a short distance before slamming into a charged particle and scattering off in a new direction. Not unlike the slow, blind stumble of light trapped inside the sun's core. Except here it was happening everywhere, throughout the entire infant universe at once. The whole sky, in every direction, would have looked like the inside of a fog too bright and too close to see through. There was nowhere in the infant universe you could have stood and seen a clear night sky, because there was, in that specific sense, no such thing as a clear sky yet to see. Darkness and clarity, The very things tonight keeps returning to hadn't been invented yet. That changed at a moment cosmologists call recombination. Roughly 380,000 years after the beginning, as the universe expanded, it cooled. And eventually cooled enough for those free protons and electrons to finally combine into stable, neutral hydrogen atoms. Neutral atoms don't scatter light the way charged particles do. The fog lifted, everywhere, all at once, and for the first time, light was free to travel in a straight line without being absorbed and re-emitted every fraction of a millimeter. That burst of newly freed light is still traveling. Some of it is arriving at your eyes tonight, stretched by billions of years of cosmic expansion from the blistering glow it started as into a faint, cold microwave hiss, detectable only with specialized instruments. Astronomers call it the cosmic microwave background, and it is, by a wide margin, the oldest light anyone will ever observe, because there is no light older than it to find. Before recombination, there was no light that could travel freely at all. This afterglow was discovered almost by accident. In 1965, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna for ordinary radio astronomy when they kept picking up a faint, steady hiss of microwave static they couldn't get rid of, no matter which direction they pointed the antenna. They checked the wiring. They cleaned pigeon droppings out of the horn, suspecting the birds nesting inside it were the source of the interference. The hiss remained, identical in every direction, day and night, summer and winter. It took a conversation with cosmologists at a nearby university who had been independently predicting that exactly this kind of leftover radiation should exist if the universe really had begun in a hot, dense state, for Penzias and Wilson to realize they hadn't found a flaw in their equipment. They had found the oldest light in the universe, filling the whole sky at once, and they were awarded the Nobel Prize in Physics for it in 1978. By the time that light reaches us, stretched by billions of years of cosmic expansion, its temperature has cooled to just a few degrees above absolute zero. A faint, uniform chill spread evenly across the entire sky. The coldest, gentlest possible afterglow of what was once an unimaginably hot, blinding fog. A European Space Agency mission, fittingly named Planck, after the physicist whose work on radiation first made this kind of measurement possible, spent years mapping that afterglow across the entire sky with extraordinary precision, completing its most detailed results in 2018. Reading the CMB carefully reveals that its temperature isn't perfectly uniform after all. Layered on top of that overall chill are extremely faint variations, patches only slightly warmer or slightly cooler than their surroundings, differing by roughly 1 part in 100,000, an almost imperceptible ripple, but a real one, left behind by tiny differences in density across the infant universe. Those slightly denser patches, however faint, had a little more gravity than their surroundings, and over billions of years that small advantage compounded, pulling in more matter, then more, until those same faint, warm patches in the oldest light there is had grown into the galaxies, clusters, and filaments that fill the sky tonight. The pattern of walls and voids we're about to spend real time on, the entire cosmic web tonight keeps returning to, is written, in miniature, in that 1 part in 100,000, reading the CMB carefully. Its temperature, and those same faint patterns of slightly warmer and slightly cooler patches, let cosmologists do something remarkable. Measure the age of the universe itself, not by guessing, but by fitting the entire history of cosmic expansion backward from today's measurements to the moment recombination happened. That age doesn't rest on the cosmic microwave background alone, either. A separate, independent check comes from a pattern called baryon acoustic oscillations, faint, regular ripples in how galaxies cluster across the sky, left behind from sound waves that rippled through the hot plasma of the early universe before recombination froze their pattern in place the same way ripples on a pond can freeze into a pattern if the water suddenly turned to ice. Large galaxy surveys, mapping the positions of millions of galaxies at once, can measure the size of that frozen ripple directly, and it provides an entirely separate measuring stick for the universe's expansion history, calibrated by completely different physics than the microwave background itself. When cosmologists compare the age implied by recombination against the age implied by these frozen ripples, the two independent methods agree closely, which is exactly the kind of cross-checking that turns a single number into a genuinely trustworthy one. The answer that measurement keeps returning, checked and rechecked against these multiple independent lines of evidence, is 13.8 billion years. Here, finally, is where every rung on this ladder connects into one honest answer. We know, from Cepheids and supernovae and the accelerating stretch of space itself, roughly how fast the universe has been expanding at different points across its history. We know, from the cosmic microwave background, almost exactly how old the universe is. Put those two pieces of knowledge together, run the expansion forward correctly instead of naively multiplying age by a single fixed speed, and the calculation lands on the same number tonight has been circling: light from the moment of recombination. The oldest light there is, originated from material that now sits approximately 46.5 billion light-years away in every direction we look, carried outward the entire time by the same stretching of space that redshifted every galaxy Hubble ever measured. Double that radius for the full span across, and you reach the 93 billion light-years we open tonight with. No longer a number taken on faith, but the end of an actual chain, rung by rung, angle by angle, candle by candle, all the way back to a wobble in starlight measured with nothing but geometry. This same fact answers a much older, much simpler puzzle, one that troubled astronomers for centuries before anyone had a real solution for it. If the universe were infinite in size, unchanging and eternally old, with stars scattered through it more or less evenly, then in every single direction you looked, your line of sight should eventually hit the surface of some star, however distant. The whole night sky, by that reasoning, ought to be as uniformly bright as the surface of a star itself, with no dark patches anywhere at all. Astronomers call this Olbers' paradox, after one of the 19th century scientists who wrote about it clearly. Though observers had puzzled over the same question long before him, the resolution turns out to be exactly the fact you now understand better than most people ever will. The universe is not eternally old and unchanging. It has a finite age, 13.8 billion years, which means there simply hasn't been enough time for light from the most distant possible stars to have reached us yet, no matter how many stars actually exist out there. The night sky is dark, quite simply because the universe is young enough that its darkness hasn't had time to fill in yet. A puzzle about the whole sky, solved by the same age and the same boundary tonight, has been building toward all along. It's worth being precise about what that boundary actually is, because it is easy to imagine it as a wall, and it is not one. The edge of the observable universe marks the limit of what light has had time to reach us since the universe became transparent to light at all. It is a horizon, not a fence, the same way the horizon at sea marks the limit of what your eyes can see, not the edge of the ocean itself. Somewhere past that horizon, by every serious model cosmologists currently trust, more universe continues. More galaxies, more clusters, more of the same cosmic structure we can map clearly on this side of the boundary, simply too far away for any of its light to have reached us yet. And in an expanding universe, some of it may never reach us at all. That raises the question tonight has really been building toward underneath the ladder of measurements. If the part we can see is already 93 billion light-years across, and it is only a boundary of visibility rather than a boundary of existence, how much more is actually out there? Is the universe, in its full extent, simply larger than what we can observe? Or does it, in some sense we haven't yet found a way to test, go on forever? Before reaching for that question directly, it's worth understanding what more of the same actually looks like, because even the structure inside our own observable horizon turned out to be far larger and far stranger than a simple scattering of individual galaxies. Galaxies are not spread through space evenly, the way stars sit inside a galaxy. They cluster. Our own Milky Way and Andromeda, together with dozens of smaller companions, form the local group. The local group itself sits near the edge of a much larger structure called the Virgo cluster, a dense gathering of well over 1,000 galaxies. And in 2014, a team of astronomers led by Brent Tully mapped something larger still. By tracking a subtle signal, not just where galaxies sit, but which direction they're actually drifting, independent of the universe's overall expansion, pulled by the combined gravity of everything around them. Tracing the motion of roughly 8,000 nearby galaxies revealed a vast basin of attraction. A whole watershed of galaxies all gently flowing toward the same gravitational valley, the way rivers on a continent all eventually drain toward the same lowland, regardless of how far apart their individual sources sit. The general pull itself had been noticed years earlier. In the 1980s, when astronomers realized our entire local group was drifting through space at hundreds of kilometers per second toward a region partly hidden directly behind the dense star fields and dust of our own galaxy's disk, a blind spot astronomers call the zone of avoidance. They nicknamed the source of that pull the Great Attractor, and for years could only estimate its position and mass indirectly, without a clear photograph of exactly what sat there, precisely because our own galaxy was blocking the view. Tully's mapping of Laniakea in 2014 placed that Great Attractor inside the wider gravitational basin. One prominent landmark inside a much larger structure, though the finer details of what exactly sits in that dust-obscured region are still being refined today. Tully and his colleagues named that entire structure Laniakea, from a Hawaiian phrase meaning immense heaven. It spans roughly 520 million light-years across and contains on the order of 100,000 galaxies, including every one of the structures we've named so far tonight. The local group, the Virgo cluster, our own Milky Way, and Andromeda, all of them simply local landmarks inside one enormous gravitational basin. There's an important distinction hiding inside Laniakea's grand name, one worth being precise about. Our own local group is gravitationally bound. Its members are pulled together strongly enough by their mutual gravity to eventually merge, resisting the universe's overall expansion entirely on that smaller scale. Laniakea itself is not bound in that same sense. It's a basin of shared motion, not a single, permanently locked structure. And cosmologists expect that the ongoing acceleration of cosmic expansion will, over enormous timescales, eventually pull its more distant members apart faster than their mutual gravity can hold them together. Even the largest gravitationally coherent structure we can currently map is, in the end, a temporary arrangement riding on top of a universe that keeps stretching underneath it. Laniakea is not even a boundary in any final sense. It has an edge only in the way a watershed has an edge, a line beyond which galaxies start flowing toward a different gravitational valley instead. Beyond it, the same pattern repeats. More superclusters, more basins, more filaments of galaxies strung across the dark like threads on a vast, three-dimensional web, with enormous, comparatively empty voids stretched between them. Some of those voids, mapped patiently by the same kind of surveys, are themselves almost too large to hold in mind gently. Regions hundreds of millions of light-years across contain only a scattering of galaxies, far dimmer and farther apart than anywhere near our own crowded little corner. A reminder that even typical is a matter of where in the web a given galaxy happens to be standing, is not an absence of interest so much as a different kind of neighborhood entirely. Mapping that structure directly took a project on a genuinely industrial scale. The Sloan Digital Sky Survey, running for more than 2 decades from a dedicated telescope in New Mexico, has measured the position and redshift of millions of individual galaxies, essentially building a 3-dimensional atlas of the nearby universe, one galaxy at a time. Plotted together, those millions of points don't form a random scatter. They trace exactly the woven, filament and void structure tonight has been describing, visible directly in the data rather than inferred from theory alone. Cosmologists call this large-scale arrangement the cosmic web, and as far as current surveys can map it, that same woven structure, basin after basin, filament after filament, continues all the way out to the edge of what we can observe. There is something worth pausing on in the shape of that web itself, separate from its sheer size. Galaxies are not scattered through the cosmos randomly, like dust thrown into the air. Large surveys that map hundreds of thousands of galaxies at once reveal long, thread-like filaments where galaxies cluster densely, strung between them like glowing cables, and enormous voids in between, regions hundreds of millions of light-years across, containing almost nothing at all. It is closer to the structure of a sponge or a lung than to a uniform spray of light, dense walls and empty chambers, repeating at a scale so large that our entire local group, Laniakea and all, would appear as a single, barely noticeable thread of that structure if you could step back far enough to see the whole thing at once. We are not looking at this web from outside it, the way you might look at a map spread flat on a table. We are one faint knot inside it, describing the pattern from a single vantage point we can never actually leave. Set against the numbers from earlier tonight, Laniakea's own 520 million light-year span, enormous as it is, comes out to only about 0.5% of the 93 billion light-year sphere we can actually observe. The largest gravitationally coherent structure our own galaxy belongs to is, itself, a small feature on a much larger map. Inside a web that keeps repeating the same pattern of filaments and voids for roughly 200 times farther in every direction before reaching the edge of what any telescope can currently see. Which brings the question back around, sharper this time. If the same kind of structure, clusters, filaments, voids, more clusters, keeps repeating all the way to our observable horizon with no sign of thinning out or wrapping back on itself as it approaches that edge, what reason is there to think it simply stops there? Cosmologists actually have a way to test part of this question, though not the whole of it. General relativity allows space itself to have an overall geometric shape. It could curve back on itself like the surface of a sphere, curve outward without limit like a saddle, or lie perfectly flat, the way a tabletop does, extending evenly in every direction. Each shape makes a specific, testable prediction about the patterns imprinted in the cosmic microwave background, because light traveling across curved space bends in measurably different ways than light traveling across flat space. When the Planck mission measured those patterns across the entire sky, in the same 2018 results that pinned down the universe's age, the geometry came back flat to within a very small margin of measurement error, the tightest constraint cosmologists have ever placed on the question. Every step of this ladder has quietly rested on one more assumption worth naming directly: that the physics we measure here, in our own small corner of one ordinary galaxy, works the same way everywhere else in the universe. Cosmologists call this the cosmological principle, and it isn't a hope or a philosophical preference. It's a testable claim checked repeatedly against everything from the uniform temperature of the cosmic microwave background across the entire sky, to the consistent behavior of type Ia supernovae billions of light-years apart, and it has held up every time. We are not special. Our vantage point is not privileged. The same laws that govern a photon's stumble through the sun's core govern the stretching of the most distant light we can detect, and every rung on this ladder depends on that quiet, well-tested confidence, holding true everywhere at once. A flat geometry doesn't, on its own, prove the universe is infinite. A perfectly flat sheet of paper is still finite if you only ever cut a rectangle out of it. But a flat, infinite universe is the simplest model consistent with everything measured so far, and nothing in the current data forces cosmologists to prefer a finite alternative over it, which leaves an answer that is honest. Rather than satisfying, the 93 billion light-year sphere we can actually observe may be an almost unimaginably small fraction of a universe that continues, in the same woven structure of galaxies and voids, forever. Or it may eventually close back on itself at some scale far larger than anything current instruments can probe. Both possibilities remain consistent with every measurement made so far. Neither has been ruled out. This is not a gap in effort or imagination. It is a genuine limit of what light, even light that has been traveling for the entire age of the universe, can tell us about a universe still busy stretching that light thinner with every year that passes. That kind of honest uncertainty is rare enough in most of what gets called science communication, and it's worth resting in rather than rushing past it. Or worse, quietly smoothing it over with a confident-sounding number that the actual data doesn't yet support. Not every question tonight has raised gets a tidy, closed answer. And the size of everything, at its outermost edge, is one of the ones that doesn't. What can be said, with real confidence, is smaller and steadier. The observable portion alone, the part light has actually had time to bring us news about, is built from real, chained, independently checked measurements, stacked 5 layers deep, angles, pulsing stars, exploding stars, redshifted light, and the oldest light there is. And every one of those layers still holds up, even where the outermost edge of the whole story quietly refuses to. There is one more honest complication worth sitting with before tonight starts winding down, and it involves the same ladder we've been climbing all along, checked against itself. Remember the Hubble constant, the conversion factor that turns a galaxy's redshift into an actual distance, mentioned briefly a few chapters back and set aside for later. Astronomers have 2 genuinely independent ways to measure it now, and for most of the last decade, those 2 methods have refused to agree. The first method starts from the cosmic microwave background. The oldest light there is, cosmologists can predict. From the physics of the early universe and the patterns Planck measured across the whole sky, exactly how fast the universe's expansion should be running today extrapolated forward from conditions 380,000 years after the beginning. That method, run through the best current physics, gives a value close to 67 kilometers per second for every megaparsec of distance, meaning, put simply, that a galaxy sitting 1 megaparsec away should be receding from us at roughly that speed, with the number scaling up steadily for every additional megaparsec of distance. The second method builds the Hubble constant directly, using exactly the ladder tonight just climbed. Cepheid variables calibrating the true brightness of Type Ia supernovae chained together across nearby and then increasingly distant galaxies to measure today's expansion rates straight from nearby present-day observations without needing any assumption about the universe's early physics at all. Careful work by the team known as SH0ES, cross-checked in recent years using the James Webb Space Telescope specifically to rule out subtle contamination in the Cepheid measurements, keeps returning a noticeably higher number, close to 73 kilometers per second per megaparsec. 67 from the universe's baby picture, 73. From the same rungs we spent tonight trusting. That is not a small disagreement dressed up to sound dramatic. It is a gap of more than 5 standard deviations, a statistical threshold physicists treat as essentially impossible to explain away as ordinary measurement error. And as of the most recent published results, nobody has found the flaw. Some cosmologists suspect an overlooked subtlety in one of the 2 methods. not unlike the two-population Cepheid error that doubled the distance to Andromeda decades ago. Others suspect the gap is telling us something genuinely new about the physics of the early universe. Some ingredient in the standard cosmological model that isn't accounted for yet. Careful independent measurements using a different kind of standard candle, faint, old stars called red giants, have landed at values sitting uneasily between the two camps, which so far has narrowed the argument without settling it. Some cosmologists have proposed that a brief, extra episode of accelerated expansion, active only in the universe's first few 100,000 years, and different from the dark energy driving today's acceleration, could nudge the early universe prediction enough to close most of the gap. It's a serious idea, studied carefully, tested against the same Planck data everything else tonight has relied on, and so far, it fits some observations better than others, which is exactly the state an honest, unresolved hypothesis is supposed to be in. Nobody tonight can tell you which explanation, if any of the current ones, turns out to be right. What can be said honestly is that the disagreement itself has become one of the most productive open questions in modern cosmology, precisely because both of the numbers producing it are so carefully measured that neither side can simply be waved away. It's worth being clear about what actually rides on settling this, because a 6% disagreement can sound abstract until you connect it back to everything already covered tonight. The Hubble constant sets the scale for every distance measured by redshift alone, which means every galaxy distance measured using Hubble's law, including some of the numbers already given you tonight, carries a small, honest uncertainty tied directly to this unresolved 6% gap. It also affects how old the universe can be calculated to be from the expansion rate alone, and how that number compares to the age measured independently from the oldest stars in the universe's earliest globular clusters, a cross-check that has to come out consistent for either version of the story to fully hold together. None of this threatens the 93 billion light-year figure at the heart of tonight's answer, which rests primarily on the cosmic microwave background rather than on the disputed local measurement. But it is a real, live seam in the fabric of modern cosmology, and resolving it, whichever way it eventually resolves, will sharpen essentially every distance named tonight by a small, meaningful amount. This is not a flaw in the ladder we built together tonight. It is the ladder working exactly as a real scientific measurement should. Precise enough, on both sides, that a 5% scale disagreement is impossible to shrug off, honest enough that nobody involved has simply picked the answer they like better and called the argument closed. A gentler version of the same honesty shows up in an even more basic question. And it is worth understanding why counting galaxies is hard at all before hearing how the count keeps shifting. No telescope can photograph every galaxy in the observable universe directly. The faintest, most distant ones sit right at the edge of what even our best instruments can detect. And countless smaller, dimmer galaxies almost certainly exist beyond that edge, too faint to register at all. So astronomers don't count galaxies the way you'd count stars in a photograph. They measure how many galaxies appear in a small, carefully chosen patch of sky, at every brightness level current instruments can reach, then use statistical modeling to estimate how many additional, undetected galaxies the pattern implies must exist just beyond current detection limits before finally scaling that estimate up to cover the entire sky. Change the model, change the assumptions about how quickly faint galaxies keep appearing as you look deeper, and the final number can shift by a startling amount even without a single new observation. None of that uncertainty comes from carelessness. It comes from asking a question at the very edge of what current instruments can actually resolve, and being honest about the difference between what was directly seen and what was carefully inferred from a pattern. A number that shifts under better scrutiny is not a number that failed. It is a number still being taken seriously by people still willing to let it change. How many galaxies actually fill that 93 billion light-year sphere we've spent tonight earning the right to describe? For years, the widely repeated number was 2 trillion. Based on a careful 2016 study, that combined deep telescope imaging with a statistical model of how many additional, far fainter galaxies must exist beyond what any telescope could directly resolve. More recently, a very different kind of measurement complicated that figure. NASA's New Horizons spacecraft, already far past Pluto and free of the faint glow of dust that brightens Earth's own sky, measured the total background darkness of the sky directly and found less unaccounted light than the 2 trillion galaxy estimate would predict. Some researchers now argue the true number sits closer to the older estimate of a few 100 billion. The debate remains open, actively worked on, unresolved as of this recording. A reminder that even something as seemingly countable as how many galaxies are there is still, quietly, an argument in progress. Even the newest instrument in this story has added its own small piece of honest uncertainty rather than closing the book entirely. The James Webb Space Telescope has found a handful of galaxies from the universe's first few 100 million years that appear larger and more fully formed than the standard models of galaxy growth expected at such an early stage, prompting real, ongoing debate among astronomers about whether early galaxies simply grew faster than assumed, whether some of the brightness measurements need refining, or whether a genuine gap exists in the current model of how the first structures in the universe came together. It is one more open thread in a field that keeps discovering. At every scale tonight has climbed through that the honest answer to, how well do we understand this, is better than ever before, and still not completely. It helps, faced with 2 well-measured numbers that refuse to agree, to remember how many times this exact shape of problem has already resolved itself somewhere earlier in tonight's story. Hubble's original distance to Andromeda was too small, until Bardet found the overlooked detail that fixed it. The tired light explanation for redshift looked plausible, until supernova light curves ruled it out directly. Even the 2 trillion galaxy estimate, treated as settled fact for years, is now being quietly reconsidered against a spacecraft's simple measurement of how dark the sky actually is. Not one of these disagreements got resolved by picking the more convenient answer and moving on. Each one got resolved by more data, more careful checking, and enough patience to let an uncomfortable gap sit in the open until someone found what it was actually pointing at. The Hubble tension is, right now, exactly that kind of gap. Whichever way it eventually resolves, it will very likely resolve the same way every earlier gap tonight did. Carefully, honestly, and without anyone needing to have guessed the answer in advance. None of this should feel unsettling in the way an unresolved argument sometimes does. It should feel, instead, like the most honest possible ending to a ladder built entirely out of real measurement. Every rung solid enough to hold real weight, and the very top of the ladder still, tonight, reaching upward into open air. There is sunlight on your skin again, or waiting just outside your window, or already promised for tomorrow, exactly the way there was at the very beginning of tonight. 8 minutes old, crossing open space at just under 300,000 kilometers a second. 100,000 years old, underneath that, still carrying the memory of its slow passage from atom to atom, out of the sun's own core. Nothing about that light has changed since we started. What's changed is everything you now know about what a number like that is actually made of. We climbed a real ladder tonight, one honest rung at a time. And it's worth feeling the whole shape of it once, gently, before letting it go. A wobble in starlight, measured with nothing but geometry, and the patience to watch a star twice a year, gave us our first true distance, 4.25 light years, to the nearest star beyond our own Sunday. A woman cataloguing photographs in a basement, noticing a pattern in how certain stars pulse, gave us a candle bright enough to reach past where geometry alone could see. That candle, pointed at a smudge of light in Andromeda, proved our galaxy was only one among countless others. The color of that other light, stretched red by the stretching of space itself, gave us a way to measure distances not in millions of light years, but in billions. The deaths of certain stars, exploding with almost perfect consistency, and the oldest light there is, freed the moment the infant universe finally cooled enough to let it travel at all, gave us both an age for everything and a boundary for how far we can currently see. 13.8 billion years old, 93 billion light years across, the part we can observe. The whole answer resting on every rung beneath it. None of them borrowed. None of them assumed. Say the whole shape of it once more, slowly. The way you might repeat a phone number to make sure it's actually settled in memory before you let it go. 4.25 light years to the nearest star, measured by watching it shift. 2.5 million light years to the nearest large galaxy, measured by a pulse of light rising and falling on schedule. Distances in the billions, measured by how far a color has drifted toward red. 13.8 billion years of age and 93 billion light years of reach, measured by the oldest light there is, arriving from every direction at once. None of it needs to be remembered precisely to have done its work tonight. It only needed to be walked through once, honestly, rung by rung, so that the next time someone says a number like that out loud, some part of you recognizes it, quietly, as something that was actually earned. That is the honest size of the part of the universe available to human measurement tonight. It is not the honest size of the universe itself. And by now, you understand exactly why those two things are allowed to be different numbers. Beyond that 93 billion light-year boundary, by every model that has survived contact with the evidence, more of the same continues. More filaments, more clusters, more of the woven structure we could trace clearly on this side of the horizon, simply too far away for its light to have reached us yet. Whether that continuation eventually closes back on itself, or simply goes on without end, remains genuinely, honestly open. Not a mystery being withheld from you. A boundary of what light itself has had time to bring us news about. In a universe that has spent the entire time that light was traveling quietly growing larger underneath it, it is worth resting, for a moment, on how strange it is that any of this got measured at all. Every rung of tonight's ladder was built on Earth, by beings who never once left this one small planet to go check any of it directly. Nobody flew to Proxima Centauri to confirm its distance with a tape measure. Nobody visited the surface of a Cepheid to watch it swell and shrink up close. Every single number tonight was reconstructed, at a distance, from nothing but the light that happened to arrive, unbidden, at the top of our own atmosphere, on nights not unlike this one. Everything tonight rested on. Every rung of that ladder was built by a small number of people, working with imperfect instruments in a short handful of centuries, using nothing but starlight that happened to fall on the right patch of glass at the right moment. A Prussian mathematician, watching one faint star twice a year for long enough to catch its wobble. A woman with a magnifying lens, paid by the hour, noticing a rhythm nobody had thought to look for. An astronomer crossing out one letter on a photographic plate and writing another, alone, at a telescope. At night, two rival teams of scientists, expecting one answer, honest enough to publish the opposite one when that's what the data actually showed. None of them set out to measure the entire universe. Each of them was simply careful, in a very small, very specific way, about one particular kind of light, and their care, stacked together, rung by rung, over roughly 200 years, is the only reason a number like 93 billion light-years means anything at all rather than being just a sound. None of them worked entirely alone, either, even when the record remembers only one name. Bessel's measurement depended on centuries of star catalogues compiled by observers who never lived to see parallax confirmed. Leavitt's pattern depended on a director willing to hire and pay a team of women to do the counting in the first place. Hubble's plate depended on a mirror ground by hands he never met, and a mountain chosen by someone else's careful survey of the sky above it. Every rung, followed back far enough, turns out to be resting on other people's quiet, uncredited care. There is one more honest thread worth pulling before we let all of this settle. Everything measured tonight, every rung, every candle, every stretch of redshifted light, describes only the part of the universe capable of sending us light at all. The part made of ordinary matter, arranged into stars, galaxies, and the space between them. That same dark energy responsible for accelerating the expansion of everything, and the unrelated dark matter responsible for holding galaxies together, appear, by current estimates, to make up the overwhelming majority of everything that exists. And neither one emits or reflects a single photon we can observe directly. Ordinary matter, the stuff of every star tonight as mentioned, every galaxy, every rung of the entire ladder, may be closer to a minority ingredient in the actual universe than the main event. We measured what we could see. What we could see, honestly, may not even be most of what's there. Consider, for a moment, what's actually doing the measuring. A human brain weighs about 3 pounds, fits easily inside 2 cupped hands, and runs on roughly the same wattage as a dim light bulb. Every atom of carbon inside it, every atom of everything you're made of, other than hydrogen, was forged inside the core of an earlier generation of stars in the same kind of nuclear furnace that spent 100,000 years walking tonight's sunlight out to the sun's surface. You are a small, temporary, and very unlikely arrangement of it, briefly organized enough to wonder, on a given night, exactly how far the rest of it extends. And organized enough, it turns out, to actually find out, one honest rung at a time, without ever leaving the ground. It is worth naming, gently, everything tonight chose not to chase, because a night like this one leaves out far more than it includes. On purpose. We didn't ask what happened in the first fraction of a second after the beginning, before even the plasma tonight described had fully formed. A real, actively studied question, and one honest enough to deserve its own separate telling, rather than a rushed final mention here. We didn't ask what dark matter is actually made of, only that its gravity holds galaxies together. We didn't ask whether other universes exist beyond our own, a question serious cosmologists take seriously, and one current evidence cannot yet confirm or rule out either way. Tonight had one job: to earn, honestly, rung by rung, the right to say how vast the observable part of this universe actually is, and to be equally honest about exactly where that certainty runs out. Everything else stays exactly where it belongs, open, waiting, worth another night entirely. Think back, for just a moment, to the storm from earlier tonight, the ordinary gap between a flash of lightning and the low roll of thunder that follows it. That same small delay, scaled up patiently, rung, by people who mostly never met each other, is the entire reason a number like 93 billion light-years means anything at all. Nothing about the underlying idea ever changed between the storm and the stars. Only the distance did. That is not a small thing to fall asleep with. It does not need to feel large or dramatic to be true. A body this size, running on this little power, reached a number like 93 billion light-years, using nothing but geometry, starlight, patience, and roughly 2 centuries of careful, occasionally rivalrous, occasionally accidental work. And it did that while never once leaving the surface of one ordinary planet, orbiting one ordinary star, inside one ordinary galaxy, itself one small thread inside a web too large to see the edges of. The universe did not need to explain itself to be measured. It only needed to be watched carefully enough, for long enough, by something small enough to be humbled by the answer. You don't have to do anything else with any of it tonight. There is no quiz waiting in the morning, no number you need to have ready to repeat. The ladder did its work simply by being climbed once. Together, from a wobble too small for the ancient world to notice, all the way out to a boundary too far for any of us to ever visit. That's the whole job finished. Everything from here is just rest. The room around you right now is a very small place to hold all of that. And it is, quietly, enough. The mattress or cushion beneath you is doing the same simple job it always does, holding your weight against a floor that is not fighting gravity so much as gently interrupting it one more night the way it always has. Whatever light is left in the room, a lamp, a screen already dimming, the last grey edge of a window, is, in its own small way, still obeying the same rule as everything else tonight. It left its source some small fraction of a second ago and arrived exactly on time, the way it always does, the way starlight always does, only sooner. Somewhere above the ceiling, whether or not you can see it tonight, the sky is still doing what it has always done. The moon's light, a little over a second old, distant planets, their light a matter of minutes or hours, the nearest star beyond our sun, its light 4¼ years old, arriving now the same way it always has, one steady photon at a time, regardless of whether anyone below happens to be awake to receive it. Andromeda, if the sky is dark enough and your eyes patient enough, a faint smudge 2.5 million years old, older than your species, arriving anyway, asking nothing of you but a clear night and a willingness to look up. None of it needs your attention to keep arriving. It was already on its way long before tonight, and it will keep arriving long after you've stopped watching. Tonight and every night after this one. You don't have to hold the number. 93 billion light years was never going to fit inside a single human mind the way a room fits inside a house. And it was never supposed to. What you can hold instead is smaller and steadier. The plain fact that distance, out there, is really just old light, still arriving. One honest photon at a time, from every direction at once, whether or not anyone is awake to receive it. That fact fits. It fits easily, right here, in a room this size, in a body this size, on a night exactly this ordinary. Notice your own breathing. If it's easy to notice without trying too hard to control it, in and out. On a rhythm, your body sets without asking your permission, the same steady interval it has kept every night of your life. That rhythm has nothing to do with light years or redshift or the age of anything. It is simply the oldest clock you own, older than any instrument tonight has mentioned, keeping its own small, private time regardless of how far the universe around it happens to stretch. 93 billion light years and one slow breath are both real measurements of something. Only one of them is yours to keep, tonight, without needing a telescope at all. There is a particular kind of comfort available in a universe this large, one that has nothing to do with feeling small in the way that word usually implies. A universe barely bigger than your own field of view would leave very little room for anything to remain unexplained, unmeasured, unfinished. A universe this large, honestly still growing at its edges, honestly still arguing with itself over exact numbers, honestly still turning up more structure the deeper anyone looks, is a universe with room left in it. Room for the next careful person with a telescope and enough patience, room for a number as familiar as 93 billion light years to still, one day, get quietly revised the way Andromeda's distance once was, the way the very shape of our own galaxy once was. Nothing about tonight's answer felt smaller for being unfinished. If anything, an unfinished universe is the more restful kind to fall asleep inside. Proof that wonder was never a temporary condition of not yet knowing enough, but the ordinary, permanent shape of actually paying attention. If sleep is still somewhere out ahead of you rather than already arriving, that's all right. Nothing about tonight required you to fall asleep exactly on schedule, any more than the light from Andromeda was required to arrive on any particular night either. It left when it left, 2.5 million years ago, and it simply kept coming, patiently, until it got here. Let your own rest arrive the same way, not summoned, not forced, just allowed. Whenever your body is actually ready to let it happen, on its own unhurried timeline, the way every other honest measurement tonight also took exactly as long as it needed to take. Think, for one more moment, about everyone who has ever done that work and how few of them ever really saw the size of what they were building. Bessel, watching one faint star's tiny shift, never learned there would eventually be a spacecraft in space doing the same thing for 1 billion stars at once. Leavitt, cataloguing photographic plates for an hourly wage, never learned her pattern would eventually measure a galaxy she never got the chance to look for herself. Hubble, crossing out one letter and writing another on a single glass plate, never learned that the expansion he'd helped uncover would turn out, decades later, to be accelerating for reasons nobody yet understands. Each of them held only their own small rung, measured as carefully as they knew how, and handed it forward to people they would never meet. The ladder was never built by anyone who could see the whole thing. It only exists because each rung trusted the ones it was standing on, and each new rung, in turn, became something worth standing on for whoever came next. That is, in its own quiet way, close to the truest thing tonight has to offer, closer than any single number. Vastness, it turns out, was never really a size to be pictured all at once. It was a patience, practiced by a very long chain of ordinary, careful people, most of whom never lived to see how far their one small measurement would eventually reach. You inherited the whole chain tonight, for free, in about 2 hours, lying down, in the dark, without needing to catalogue a single photographic plate yourself. That is worth something. Not a size, a kind of quiet trust, past rung to rung, star to star, all the way from a wobble too small for the ancient world to see, to a boundary too far for any of us to ever actually visit. Let the numbers go now. Let the ladder go too. The wobble, the pulsing stars, the exploding ones, the stretched red light, the oldest light of all. You don't need to carry any of it forward from here. It will still be true in the morning, waiting exactly where you left it, the same way it was true 100 years before you were born, and will stay true long after. All that's left tonight is the weight of your own body, settling, and the quiet, ordinary fact that somewhere above you, whether visible or not, an old light is still on its way here, in no hurry at all, the way it always has been. The universe will still be here when you wake up. So will we. Good night.